We'll start with what is neural network actually. So the today's task is we are going to solve for the genetic algorithm. Using genetic algorithm, how we are going to optimize the weight of a neural network. So we'll take one problem and that problem is like a personal loan classification problem. So we'll be having a data set related to the personal loan data set, whether the person is going to take the loan or not based on the certain features. So we'll try to fit a neural network model for that particular data set. So when we try to fit a particular neural network model to the data set, we'll try to optimize the weights. Basically, neural network will have certain amount of weight parameter, right? So that particular weight parameter can be updated in two ways. Like we can update it using gradient descent algorithms or any other conventional techniques. So another way of optimizing the weights of the neural network is like evolutionary computing methods. So one of the evolutionary computing methods or search-based algorithm which we are going to discuss today is a genetic algorithm. So first I will talk about what is a neural network at an higher level overview. So then after seeing what is actually a neural network is like a brief overview, we will see how to use a genetic algorithm to interlace the weights of the neural network so in an efficient way. So that is what we are going to try to see today with the hands-on session of coding. So we'll just move into what is a neural network. So neural network basically it's like a hierarchical feature learning method where we'll be having a set of neurons and set of layers. Okay. So we'll talk about what is an input layer. So neural network basically consists of a different kinds of layer. So the first layer where you will be supplying your features is what we called as an input layer. For example, you have a data set containing like let us take this particular data set, education. So education is one feature, and age is another feature, feature, and salary is another feature. So for example, like next one is risk prediction. So this is a predictive variable which we are going to predict whether based on this particular three features we are going to predict whether the person is eligible for getting a loan or not. So these are the features which we'll supply to the model to get the output, the risk predicted one. So this is what data set we are going to take, like it's a miniature version of the data set which I'm trying to explain you. So for the input layer will be having a three nodes. Why three nodes? Because we have a three set of features. So to have a three set of features we will be having a three nodes in the input layer. Then you will be having a set of hidden layers. Then you will be having a output layer. So hidden layer or those kind of layer which are directly connected to your input layer. Hidden layer size can be anything, like size I'm meaning the number of nodes. So the number of nodes is like an hyperparameter in each and every layer. You can tweak the hyperparameter to get the optimal results for any task in hand. So for example, let us take we are having a we consider, let us say we are having our 11 features. So in the data set, so I'm going to define my neural network architecture in such a way that I'm going to take 11 input nodes, 11 nodes in my input layer. So this is 11. So then I'm going to take, for sake of simplicity, let us take the hidden layer size as 8. So I'm going to take 8 nodes in my hidden layers, and I'm going to have my output as a single node. Because why single node? This particular single node will be having a two representation values. One is 0 and another one is 1. So 0 represent is not eligible to take loans and 1 represent is eligible to take notes. So now these features have been connected with each other with the synaptic connections called weights. So each and every layer are connected, each and every nodes in the layer are connected to weights. So for a fully connected neural network, each and every nodes are connected with each other. So if you take a sparse connected neural network, some of the layers may not be connected, some of the nodes in the layers may not be connected. So that is not a point of discussion right now. So we'll take a fully connected neural network. So this fully connected neural network where you will be having a nodes in the input layer and nodes in the hidden layer and nodes in the output layer. Each and every nodes in the layer are directly connected. So basically, okay. So this particular connection is called as weights. So this weights is going to represent how strongly these two features are connected with each other. For example, let us zoom this one. Okay, so this is one feature, this is one feature, this is another feature in the hidden layer. For example, this weight is 0.7 and this weight is 0.1. So this says that this feature is highly contributing to this particular feature as compared to this feature. So this is how we can interrupt those things. So in this case we are trying to say like every nodes are connected to each other. Now let us try to answer this question. We have been having 11 nodes in the input layer and 8 nodes just present in the hidden layer. How many total number of weights will be having in the first layer? So 11 nodes we are having in the input layer and 8 nodes we are having in a hidden layer. So the total number of weights is going to be 11 into 8, which is 88 weights is going to present between your input layer as well as first hidden layer. So then now we are moving to the hidden layer to the output layer, in which all the nodes present in the hidden layer are connected to your output layer. So basically the number of nodes which is present in your hidden layer is 8 and the number of nodes which is present in your output layer is 1. So basically you're going to have 8 into 1, totally 8 weights in your hidden layer to output layer. So this is what we are trying to, this like 88 plus 8, which is going to be sometime 88 plus 8 weights, we are going to trying to optimize. So to better fit of the data using a evolutionary computing models. Now Let us take this one. How this particular forward propagation is how forward propagation will take in place in neural network. That is what we are going to trying to see. For example, let us take a simpler example. So I am having a three nodes in my input layer and two nodes in my hidden layer and one node in my output layer. So these are my connections. Like these are my weights. So this is a fully connected neural network. Okay, so now we'll try to calculate the total number of weights between the input layer and my hidden layer. So basically I'm having a three nodes which is present in my input layer and two nodes present in my hidden layer. So total number of weights is six. So now let us try to calculate how many amount of weights present between your hidden layer and output layer. You basically having a two nodes in your hidden layer and one nodes in your output layer. Basically you're going to have two. So the total number of weights in your neural network is 6 plus 2, which is 8. So we are going to trying to optimize this kind of eight set of weights to get a better result. In the better results, what I'm meaning is the better accuracy. So if you're trying to calculate the classification model, you'll be considering of an accuracy. If you're trying to calculate the regression kind of model, you'll be dealing with the losses. So now I'm trying to calculate. Now I'm trying to dealing with the classification model. So I'm going to make my metric as an accuracy. I need to get maximum number of maximum value of an accuracy for this set of weights. So that is what I'm going to trying to make from this neural network at the end of the day. So we'll be having an eight weights, that is eight learnable parameters. So now how the forward propagation happens in neural network. So we'll see. So for example, okay, let us take this for the sake of simplicity. This six weights I am representing as W1. This two weights I am representing as W2. Okay. Now the forward propagation going to happen by using this simple formula. You have your Z1. So this is the first layer. So Z1 equal to nothing but your dot product of your x. X is nothing but your input, like x1, x2, x3 will together represent as x. So x into w1 plus bias. So this is what you are going to calculate as z1. Now this particular z1 is need to pass into an activation function. What is activation function? Activation function in a higher level overview, we can treat this as a non-linear function, which is going to capture your non-linearity in your data. So now you're going to calculate E1. E1 is an activated value where you'll be passing some activation function of Z1. You'll be passing your Z1 to the activation function. So this is what you'll be getting at this particular node. Now, this particular node, that is A1, is going to multiply with your W2 plus some bias. That is going to give you Z2. So this is Z2. So Z2 is nothing but your A1 is going to multiply with V2 plus some bias. So this is what your Z2. But I need A2. What is A2? A2 is nothing but activation function will be passed, where your Z2 will be passed into an activation function, will give you an A2. So this is the A2 is an predicted output. Now how we are going to calculate your accuracy? You are going to calculate your accuracy. For example, Y is your actual one and Y bar is your predicted one. So then you are going to calculate the accuracy set between Y and Y bar. You just say total number of correct predictions by total number of test cases or total number of records. So that is what the formula which is used to calculate your accuracy metrics. So you will try to calculate an accuracy. Now you will be training your weights in a such a way that, because weight is a learnable parameter, you are going to train your weights in such a way that you will be maximizing your accuracy. Okay. So I need to optimize this weights, right? This weights we can term it as an active learnable parameters. Now we are going to trying to activate. Now we are going to trying to learn this weights. Now we are trying to optimize this weight. So as I said earlier, we have two different methods to optimize this weight. So initial method we'll be trying to back propagation using a gradient loss function, gradient descent, and there is a different kind of methods which is available, and you have a different kind of optimizers. The next one is like your evolutionary computing method. This particular evolutionary computing method involves genetic algorithm, particle swarm optimization, and colony, gray wolf optimization, and many more. Now we are going to see how genetic algorithm will be helping interlacing the weights of a neural network. So that is what we are trying to see today. Now, I just move into the genetic algorithm, a quick introduction. So as you all know that genetic algorithm is like a search-based optimization techniques, which is going to operate on the basis of genetics and natural selection, right? So it's going to find an optimal solution. So what is an optimal solution? So optimal solution is like you have a set of solution, which solution is producing a best set of output values. That process will be called, that output will be called as an optimized output. So the process of getting an optimized value is called as optimization. So basic terminology which we are going to see in this kind of genetic algorithm is like your population. What is a population? Let us say I have a problem in my hand. What are the possible solution for that particular problem? I will be termed as an population. So if I have a problem in my hand, my problem in my hand is like I need to optimize my weights in a neural network. So what are the possible kind of weights I'm going to represent? That particular possible kind of weights will become as a population. So then what is meant by chromosomes? So we have n set of solutions. Like so for each and every set of solution in the population space, we'll be calling as an chromosomes. Let us say I have a solution 1, solution 2, solution 3, and so on. Each and every solution I can term as a chromosomes. This whole I will be termed as a population. What is meant by gene? So for example, let us take this whole case. This whole is a set of like populations, and each and every individual element we will be calling as a chromosomes. Okay. So what is a gene? Gene is like one position. For example, I'm taking the index position 3, so this is called as a gene. What is meant by allele? It is a value which is present inside the gene is called as an allele. So this is what the basic terminology which we need to know in order to go into the genetic algorithm. So next set of terminology is genotype. So genotype is nothing but we are doing all the set of problem computation in the computation space, right? The solution or need to represent in a such a way that the computers can easily understand. So the process of representing a solution in a such a way that your computer can understand is called as a genotype. What is phenotype? The phenotype is a real valued representation. What is the problem which is represented in the real space or real world? So that type of representation of the problem which we called as a phenotype. What is meant by decoding? So decoding is a process of transforming your genotype to phenotype. So your genotype solutions are transformed into the phenotype solution. That process we called as a decoding. So then reverse of the decoding we will be calling as an encoding. That is your conversion from your phenotype to genotype. That process we will be calling as an encoding one. So this is the like a high level overview of a diagram. So genotype is a computational overview, phenotype is an actual space. So you have encoding and decoding, which we'll be using for computational purposes. So next one is a fitness function. What is fitness function? Fitness function is a function. Okay, let us say you're having a 100 set of solutions, which is going to solve the problem. Now we need to find out which set of solution is the best to solve the problem. In order to evaluate which set of solution is best to solve the problem, we'll be using one set of function. That kind of function is known as a fitness function. So this fitness function is used to take your input and it's going to calculate some mathematical work. Okay, so that is we going to define based on the problem which we're going to solve in and. So that particular output will be mapped in such a way that you need to take the maximum value or your according to your objective function which produces a maximum or minimum value you'll take as a best set of an output. Okay, so what are the set of genetic operators which we are going to perform in genetic algorithm? Okay, so we have a different kind of genetic operators such as crossover, mutation, selection, and etc. We'll see one by one. So this is an algorithm for the genetic algorithm. Initially, you'll be initially at beginning you'll be initially a set of population. Then you'll be finding a fitness for each and every population based on your objective function. So that objective function may vary according to the type of problem which you're dealing in. And okay, let us say I'm setting my termination condition like for an 100 epochs or 100 iteration. Till 100 iteration, I'm going to repeat this process. What this process actually means, first we need to select a parent. How we are going to select the parent? There are different techniques which we are going to deal to select the parents that we'll discuss in the upcoming slides. So next one is a crossover. What is a crossover? Crossover is like a genetic operators which you're going to perform. Then after crossover, you'll be getting a mutation operation. Then you'll be calculating the fitness function. Then you'll be finding a survival selection and you're going to return the best. How we are going to do? We will be seeing in a minute. Okay, now let us see. We are going to look into the genetic operators. Like, how do we represent a solution? Like, how do we represent the problem? So there is a three different ways of representation. One is a binary representation. Another one is a real value representation. Another one is an integer representation. How you are going to represent a solution? So that is what we are going to calculate. That is what we are going trying to see in genotype representation. For example, if a binary representation is going to consist of two set of values, one is 0 or 1. It's a kind of label or label encoding or one not encoding. You can think of that particular level. Next one is like a real value representation. You're going to have a real value representation. In terms of neural network, which we are going to represent the weights, right? So we are be representing our weights in the form of real valued one because I will be having a discrete set of values, right? So that is a real value representation. Next one is like integer representation. For example, let us say you're having your four directions, okay? So north, south, east, and west. How we are going to encode them? You'll be giving a value of north as 0, 1, south as 1, east at 2, and west as 3. So depending on the data, you're going to encoding them accordingly. So that is an integer representation or mapped representation, whatever ways you can call it. So now we are going to deal with population. What is population? As I said earlier, the total number of solutions which are trying to solve for the solution, trying to solve the problem, that particular set of solutions together we called as a population. So guys, remember, you cannot able to keep your population like extremely high because that will slow down your genetic algorithm process. While the smaller population will also not easily converge. So you need to take the population size in a such a way that it need to balance between your convergence as well as like your hardware consumptions. So your population size should be in a deserved manner. You can treat this population as an hyperparameter. So this hyperparameter, you can fix it or figure it out using a trial and error method, right? So next one is like your population initialization. How do we initialize a problem? Okay, you're telling that the population or those kind of ones which is used to solve your solve your problem. How we are going to define a population? How we are going to initialize the population? So that is one of the important question we are going to trying to solve. There are two ways basically. One is a random initialization. Another one is a heuristic initialization. Okay, random initialization. You just put np.random or any function like random function. So that particular population is going to be full of random, right? So that is a random that we're going to call it as a random initialization. Next one is like heuristic initialization. Okay, you'll be having some basic knowledge. Okay, in the mari like if you have a certain of weights or certain amount of problem which you're trying to solve, you'll be having some basic knowledge. So with the help of some basic knowledge, you are going to initialize the population. That kind of initialization technique we'll be calling as an heuristic initialization. So these are the two ways in which you can initialize a population for the genetic algorithm. Next one is like fitness function. I told already. We'll be having a set of solutions, like set of populations, like a set of chromosomes, right? We need to figure out which chromosome is the best chromosome to get the objective values. So that particular value which you can be figured out using this particular function that is called as a fitness function. This fitness function is also known as an objective function, right? So this particular fitness function is going to vary depends on the problem which you are trying to solve on. And for example, if you are trying to solve the neural network weight optimization, our fitness function is going to be my accuracy metrics, right? So I need to get the maximum set of an accuracy for any set of weights which I'm applying to my neural network architecture. So let us say I have five different set of weights values. I'll be applying five different set of weights value to my neural network. I need to get the set of weight which is going to produce my maximum of accuracy. So that is what we needed at the end of the day, right? So my fitness function for the neural network optimization is going to be my accuracy metrics. Next one is like how do we select the parents, right? This is one of the important questions. As we see, we will have these steps. The next step in the process is like parent selection. How we are going to select the parents? There are various ways to select your parents. One is a roulette wheel selection. Another one is stochastic initial sampling, tournament selection, rank selection, random selection. So there are many ways to select your parents. So the roulette wheel selection is like you have a point. So you generate some random number. You just rotate this roulette wheel. So if you just rotate this roulette wheel, you're going to get the value like the chromosome which have a maximum amount of fitness value as a maximum probability to end up, right? So if you're just rotated, like you see this half of the portion is covered by this particular chromosomes. So we are going to get the value which has a maximum value, which is going to fall on this particular point. So that is what your roulette wheel selection. So next one is stochastic universal sampling. You're going to have two pointers instead of fixing one set of pointer. You're going to have a two set of pointer. Next one is like tournament selection. What is tournament selection? You have a set of chromosomes, right? You have a fitness value for each and every chromosomes, which you calculated by applying to the fitness function. Now let us say I'm going to define the value of k as 3. In this set of values, I'm going to take three random values. The three random values. I'm not going to take any heuristic mapping. I just take three random values. For example, let us say in this case, I'm taking A, E, and T. Now, according to A, E, and T, whichever chromosomes having a maximum fitness value, we are going to take that particular value, like 5, 2, and 2. So, which is having a maximum fitness value, the chromosome A is going to have a maximum fitness value. I'm going to take as a A as a parent. So, this is what we will be dealing with tournament selection. Next one is rank selection. Rank selection is like the individual which is having higher fitness value automatically selected. The individual which is having a lower fitness value will be eliminated from the population. So this is what we are trying to see in rank selection. We are going to rank the chromosome according to their fitness value, and we'll be taking a k set of ranks. If I want to take three best parents from the population, I will be taking top three. So that is what the rank selection. That is what we are also trying to implement in neural network weight optimization. We are going to do a rank selection. Rank selection says that I'm going to take whichever weights have a maximum accuracy, that particular weights only I'm going to take for the next set of evolution. So that is what a rank selection. Next one is random selection. I don't go for any mapping. I just put it simply random. Like simply random means I'm just taking the chromosomes in a random fashion. It may end up with like good values or it may end up with the bad values. I'm not know because it's fully random. So this is a random initialization. Now we will be looking into the genetic algorithm operators. Like we have two different operators, right? One is a crossover, another one is a mutation. So the crossover is nothing but you'll be selecting a two parents and you're going to reproduce a new child. How we are going to do? There are different crossover operations are there. One is a 1 point crossover, another one is a multi-point crossover. Okay. So for the 1 point crossover, you just take a random index. Okay. So I think wait, I'll zoom in. Okay, so these are the set of two chromosomes, right? One is like 0, 1, 2, 1, 3, 4, 5, 6, so 1, and another one is 5, 7, 8. Okay, I'm going to take a random index. For example, the index is like fourth index. Okay, I just place my pointer over here. So after placing the pointer over here, this particular thing will goes here, and this particular things will come this. So this is called a single point crossover. There is another variant which is called as multi-point crossover. You just take a 2 points in random. After taking a 2 points in random, you just swap it. For example, at this case, you see we have a 3, 4, 5, right? Another one is 4 to 3, right? So this 4 to 3 is going up and this 3, 4, 5 is going down. So this is what we are trying to do in a multi-point crossover. So there is a variation, like there is a different kind of variation of a genetic algorithm operators are there. You can explore it like later on whenever you need a different operations. Like next one is like your genetic algorithm. Next one we are going to see is a mutation. What is mutation? After doing a crossover, you get a child, right? You're going to take some random values in the chromosomes. You will be getting some child value, right? Child chromosomes. So in the particular child chromosomes, you are going to randomly tweak minute values to get some randomized values, like randomized population, so to get a better individuals. That is what we'll be dealing with evolutionary computing at the end of the day, right? So you'll be having this bit flip, like okay fine, this is my chromosome. I will be taking some random index. For example, if I take this particular value, if I take this particular value, what I'm going to do is I'm going to swap the bit. If it is 0, I'm going to make it as 1, and vice versa. For example, if it is 1, I'm going to make it as 0. So this is what we'll be calling as a bit flip mutation. This is only possible when my population representation is in a binary value. It is not possible when I'm going to represent in my integer value or something like that. So this is only possible if my representation of the problem or chromosomes in a binary values. So that is what we'll be talking in a bit flip. And next one is like a swap mutation. Swap mutation, instead of taking a single index, I will take two index. Okay, so and I will take two index, and what I'm going to do is I'm going to change this position. For example, 1, 2, 3, 4, 5, 6, I will take 2 and 6, and I'm going to swap these two values. Like it's a kind of swapping operation. So 1, 6, 3, 4, 5, and 2 will come over this, and 7, 8, 9, 0. So this is a swap mutation. Then next we will be having a scramble mutation. Scramble mutation says that you'll pick a set of start and stop value, and you just scramble this in the sense you can reverse it. You can change the order. You can use like any value multiplication, like each and every value you just multiply with 0.01 or something like that. You can do anything like that. Is a scramble mutation. If you take the same thing, you pick an index and just reverse it, that is called as an inverse mutation. So there is a various flavors of mutation operations are there. You can work it or not, whatever mutation you need. So next one is like a last step we will be dealing with is a survey selection. What is a survey selection? Okay, I am defining my population size is going to be 300. So at each and every iteration, I need to get the 300 only. So for example, if I'm producing 20 child, then it will become 320. I need only 300. So I need to eliminate some of the parents, right? Some of the parents or some of the chromosomes in the population, right? So in order to do that, I will be doing some technique called surveyor selection. So this surveyor selection, okay, to be clear, I will be explaining it again. We have a population size will be initialized as 300, okay, at the beginning. If you start selecting the parents, you'll do same process. You'll just say like you're selecting a parents and you're creating your offsprings, right? So for example, you are creating a 20 offsprings. Now what is the size of the total population now? 300 parents plus 20 offsprings, which will become 320. But my algorithm says that the population space should remain same, right? Initially we took 300, so it should be 300 at the end of the algorithm. So I need to eliminate the change, like I need to eliminate 20. How am I going to eliminate the 20? So that is what the technique we are going to deal with today is called a surveillance selection. So surveillance selection is a crucial one, because why it is a crucial one? You don't want to eliminate the individual which is the best performing one. Anyways, if you take any organization, the organization is not going to fire the employee who produces a best output, right? So that is what we are going to do it here. So we are not going to eliminate the individual which is a best performing candidate. So we are going to eliminate the one which is least performing in the population. That is what we are going to do in a surveillance selection. So there is a two ways of surveillance selection. One is the age based method, and another one is a fitness based method. So in the neural network weight optimization, we will be using a fitness based method, not the age based one. So now you see, okay, fine. We have a fitness-based selection, right? So you have a different set of chromosomes, and these are the set of an offsprings. So these are the parent population. So you need to replace these two within a population. If you replace these two in a population, here there is already 10, but here there is a 2. This will become 12. But my population will need to remain 10 as it is, like kind of the algorithm, right? I need to eliminate the two of thing. So how am I going to do? I will be replacing some of the twos from this population based on the criteria of fitness. So any individual or any chromosomes which is having a least fitness of K. For example, if this K is 2, because I have two offsprings, right? So I'll be taking the least two fitness values chromosomes. In this case, if you see 110, there is a 2 1, right? So you can take any one. There is an tiebreaker. You can choose any one. So for example, I'm taking 0 and 1. So now I'm going to replace the chromosome P1 and P10 with my C1 and C2. So if you do this kind of things, you will be getting a population space which is a best performing candidates, right? So that is what I needed at the end of the day. So this is what the fitness based selection method. There is another method. This is what we are going to implement today in neural network weight optimization. There's also another method for your information. That is an age based calculation. So how many times these chromosomes retain in my algorithm, that many times I will be adding my age values. Okay. For example, this chromosome P4 is retained in my algorithm for the 10 iteration, then the age of the P4 will become 10. This P7 retains in my algorithm for the 9 times or 9 iteration, the age will become 9. So I'm going to replace the individual which is having a highest age. I'm going to replace the individual, like the old individuals, like highly aged individuals. So this is another one method of replacing your chromosomes. So that is what we are not going to deal it today. So we'll just see how this fitness based selection is going to happen. So to be summarizing one, so what we are going to trying to do in a neural network is like we are going to define okay, first we need to define the population. What is a population? Population is a weights in the neural network. We'll be having a so many number of weights, right? For example, in our neural network, what we discuss, we'll be having 11 set of features in the data set, and we'll be having an 8 hidden layers and one output layer. This hidden layer calculation is here hyperparameter. You can take n number of nodes in the hidden layer. For a sake of simplicity, I'm taking 8. So how many total number of weights is going to present in my neural network? So that is going to be 11 cross 8. Because why 11 cross 8? Because 11 nodes is present in my input layer and 8 nodes is present in my hidden layer. So theoretically 11 into 8, which is 88 in this particular layer. And in this layer, you'll be having a 8 hidden nodes and one output node plus 8. You're basically going to have 96 weights. So you're going to optimize a 96 weights. So that is what we will be trying to do. So you're going to define a population. That population is going to consist of 96 cross 1 vector. So 96 cross 1 vector says that, for example, if I take a 300 population, you'll be having a 396 cross 1 vectors. So 396 weights, 300 cross 1. That is basically, this shape is 300 cross 1. The internal vector is 96 cross 1. Why 96 cross 1? Because I need 96 weights to optimize my neural network. So each and every weight is called as a chromosomes and weight values is a gene and allele. So next process is fitness function. What fitness function I'm going to define for my neural network architecture is my accuracy metrics. So for any weights I get a most amount of an accuracy, I will be retaining in my population. That is my fitness function or objective function, whatever you say. So next one is like what is my genotype representation? My genotype representation is going to be real valued because this is a weights. Weights can ranges from minus infinity to plus infinity. So I will be taking as a real valued representation. Next one is like what is the initialization method we are going to follow? The initialization method we are going to follow is a random one because initially we just randomize and we'll optimize it. We'll try to optimize that one. So next is like parent selection. In this type, parent selection is a rank selection. What rank selection says, whatever the individual which has a higher fitness value, I'm going to take that one. So that is a rank selection. For the crossover, we'll be taking a 2-point crossover. And for the mutation, we'll just multiply some of the values in between. That is a scramble mutation we're trying to follow. And surveillance selection, we'll be taking a fitness-based method. So whichever the weights will be giving an highest amount of an accuracy, that is highest amount of fitness value. So I'll be taking that particular weights. So this is the overview of what we are going to see in coding. So for the coding part, okay, fine. So what data set we are going to trying to solve today is like a bank personal loan modeling data set. So this data set is going to contain a different features. So some of the features are irrelevant ones. So we'll try to neglect those kind of features. So we'll take only the features which are very important. Okay. So my like a predictive column, like a dependent feature is going to be my y. So y is like a personal loan. That is what I'm going to predict it based on the all the features. So I'm just importing the packages. So we are using a numerical Python for the manipulation, and we'll be importing the pandas for the dataset reading, and random. As we see, evolutionary computing is full of randomized methods, so we import random. And I'll be importing two helper functions like from sklearn. There is one is an accuracy score, another one is like a classification report. So to to benchmark our performance, we use a classification report, and for the fitness function, you'll be using an accuracy score. So next one is like pre-processing. We need to pre-process the data set. So to pre-process the data set, we'll be using a standard scaler. So Next one is like train test split. So we need to have a certain amount of data, like 70% or 80% of the data for the training purposes, and 20% of the data for the validation or testing purposes. So that is what we need to know about it. Like, okay. So now coming to the dependent variable and independent variable. The independent variable are those variables in which the model is training on. So that we call it as an independent variable. And dependent variable is the one which is being trained on. Okay. So independent variable are the variables which are like you use to train the model to predict your y. So in short, we can say like that. So I'm just reading the data. Okay. So this particular data is like bank loan modeling data, and I'm getting the first 5 rows to see whether my data is containing any values or not. So this particular data is an imbalanced one. Okay. So I'm not using any oversampling or undersampling techniques to avoid like balancing and all. So it's an imbalanced data set. If you have time, you can use a smooth technique to oversample the data. So that is out of scope today. So we just use this data as it is. So and I'm dropping some of the values, right? Okay, I don't need this ID and I don't need this zip code. Okay, so I'm just dropping this value and I'm making this like X as a this particular value and Y as like a personal loan data. So next one is like I'm splitting the data into the training and testing part. So I'm just make sure that 80% of the data which I'm going to test train the model, and 20% of the data which I'm going to test the model. So I'm just making the X train and Y train test. Next one is like feature scaling. Why do we go for a feature scaling? So we will be calling for a feature scaling because if one feature is a larger scale than any other feature, it can dominate the distance metric and it can influence the model, right? So the normalization method, which we are trying to like helps to prevent this dominance. For example, you can have like a data set which contains of your age and salary, right? So the salary can be in lakhs or 10 lakhs or 1 crore, something like that, but your age cannot be more than 120 if I'm not wrong. So that particular there is a dominance in scale of range of variables. So that is what we're going for, a normalization kind of things to prevent the model biasing. So now I'm using a technique called like a feature scale. Now I'm using a technique called standard scaler. So this standard scaler is nothing but a z-score normalization, which is going to rescale your features in such a way that this take the property of a standard normal distribution with a mean of 0 and standard deviation of 1. So you just import the standard scalar object. So then you put a fit transform of x train and x test. So you just scale your data. And now I am going to define the class for the neural network. Okay, this is the constructed method. So now what I said is right. We need an input size, right? What is an input size of my neural network? So in this case, my input size of the neural network is 11 because I'm going to have 11 set of features. So we need to define the input layer size, and we need to have a hidden layer size, and we need to have an output layer size. So for this case, we will take the hidden layer size as 8 and output layer size as 1 because we will be having a binary classification, either 0 or 1. So one node is enough to represent the output. Next one is like this neural network will be having a set of weights. So that weights I'm representing here. So as I said right earlier, the W1 is going to be your first layer weights, which is going to multiply your input size into hidden size 1. That is 88 weights is going to take a place as W1, and W2 you'll be having a 8 into 1, basically 88 weights. So the total number of weights is 88 plus 8, which is going to be 96. I'm just mapping these weights in a such a way that okay, so this is a slicing method. So this method says that your W1 is going to be like W1 is going to be 11 into 8, right? 88 weights you are going to represent for the first 88 weights is going to be a W1. So the shape of W1 is going to be input size into hidden size. That is 11 cross 8. So this is what I'm doing in this particular place. Same for the W2, your shape is going to be 8 cross 1. So how 8 cross 1, you're going to have 8 weights, the last set of 8 weights, like W1 size of 1 to W1 size of 1 plus W2 size of 2. So this basically says that your 89th weight to you're going to have a end of the weights, like you have a 96 weights, right? So that particular weights will be represented as W2. I'm reshaping to hidden size 1 into output size, like basically 8 cross 1. Now I need to define my forward propagation. As I told, right, forward propagation is nothing but a dot product. We just forgot about the bias right now. We don't need a bias right now. So you just go for the forward propagation. So forward propagation, what we are going to do, we are just, as an initial step, we go calculate the Z. Z is nothing but your dot product of X and W1. Then you'll be passing into an activation function. Okay, in this case, I will be introducing into the two activation function. One is a ReLU, rectified linear unit. Another one is like sigmoid. What is ReLU? ReLU is like nonlinear activation function. This ReLU is going to have like this. So basically this going to act like you have a max of 0 comma 1. So max of 0 comma x, sorry. So whatever value you are getting which is greater than x, you just represent the value as it is. If the value is less than 0, you put 0. So that is what the ReLU activation function says. So next one is a sigmoid activation function. Sigmoid activation function is going to squeeze your values between zeros and 1. So your skews your value between 0 and 1. If your value is extremely negative, this is going to map it as a 0. And if your value is going to be extremely positive, it's going to map into 1. The formula for the sigmoid function is 1 by 1 plus e power minus x, where x is your input which you're going to fit to the model. For this the particular thing, your formula is f of x is nothing but max of 0 comma x. So these are the two set of activation functions which you're going to use right now. So ReLU I'm giving for the hidden layer activation function. As an output layer, what we're going to trying to do is like you're going to calculate Z3. Z3 is nothing but dot product of your A2 with W2, and you're going to pass it to the another activation function that is a sigmoid function because it is an output layer, right? So in the output layer, you're going to keep a threshold. If a value is just less than 0.5, you're going to treat it as 0. There is no loan taken. If a value is greater than 0.5, you're going to treat it as 1. It's a kind of thresholding. So that is what we are going to do in this sigmoid. So and I'm returning the output, right? So and I'm just defining the formula for the activation function. We are going to use a two different activation functions, right? One is a sigmoid activation function. It is going to take the value of 1 by 1 plus e power minus x. At this place, I'm giving a parameter as z. So this parameter of z will be like 1 by 1 plus e power minus z. So next one is a ReLU. ReLU is nothing but I told you is the maximum of 0 comma x. In this case, my parameter is z. So it's going to take the maximum of 0 comma z. So this is the two activation function I'm defining. Now I told already like the layer size, right? So 11 is the input layer size and 8 is a hidden layer size, and your 1 is a like output layer size, right? So the total number of weights is going to be layer 0 size of 0 into 1. That is 11 into 8 is 88. That is a W1 plus layer size of 1 into layer size of 2. That is 8 into 1. That is W2, which is 8. So the total number of weights is going to be 88 plus 8, which is 96. X is a fitness function. As I said you, what is a fitness function? Fitness function is like accuracy metrics which you're going to use. So our objective function is I need to get my weights in a such a way that I need to get the maximum value for my weights, like maximum accuracy I need to get for the following weights. So that's a fitness function definition over there. So this fitness function definition says that I will be supplying my weight to the fitness function, and I'll be adding this weight to my neural network. Thus I'm substituting my weight to the neural network, and I just forward propagate it, and I'm getting my y pred, right? Y pred is nothing but the predicted value. Now I'm going to calculate the accuracy score of my predicted one as well as trained one. So the trained one is like ground truth, okay? For example, excuse me. For example, if you take like this, okay, so this is your y pred and this is your y true. Y pred is 0, 0, 1, 1, 1, 0. So this is nothing but this is going to be 0, 0, 1, 1, 1. Okay. So what is the accuracy? Accuracy is like total number of right predictions, right? So by total number of prediction. In this case, what is the total number of right prediction? This is right. This is right. This is right. This is right. But this is wrong, right? So my total number of right prediction is 1, 2, 3, 4. So 4 divided by total number of prediction 1, 2, 3, 4, 5. So 4 by 5 is my accuracy score. So this is how we are going to calculate. How we are going to calculate? We are going to calculate 1 second. Okay. So how we are going to calculate? We are going to calculate in such a way that we will be taking a y pred and y true. What is y true? Y true is a ground truth and y pred is a predicted one. So I need to get a maximum set of an accuracy. So I'm defining the fitness function over here. So next, like a parameters definition for a revolutionary computing, that is a genetic algorithm. Here I will be defining my population as a 501. This is an hyperparameter, you can play on it. So I'm defining the population size as 500, and like I'm defining the number of epochs or number of iteration I'm going to run the model, that is 20 over here. And I'm going to define the pool size. What is the pool size? Pool size is number of offsprings have been generated on each and every iteration. So here 20. If I set 20, what I'm going to do, I'm going to eliminate the 20s from each and every iterations, right? So next one is like initializing population. As I told earlier, what initialization method we are going to use? We are going to use a random initialization method. So the random initialization method says that, okay, fine. So I'm going to randomly initialize weight. How am I going to randomly initialize my weights? I'm going to randomly initialize my weights in a such a way that it's going to follow the random uniform distribution. Basically, my value is going to be -2 to +2. So this is going to take a lower limit as -2 and a higher limit as +2. And how many weights in a set I'm going to have? 88 plus 8, 96 weights I'm going to have. So the total weight is calculated here. So there is 88 weights, right? 88 plus 8 weights, 96 weights, right? So I'm going to define a 96 weights, 96 weights. So and I'm going to do it for 500 population because I'm going to have a 500 population. So I'm going to generate 500 values of 500, like I'm going to generate the 500 sets, okay, for the 96 cross 1 weights. So this is what I'm going to do, initializing population. So this is a random initialization. Next one is like, okay, these are the helper function. We'll come to this later. So what I'm going to do, now currently my current population is a random value, right? So what I told you, like the parent selection method, what parent selection method we are going to figure it out. So we are going to try the parent selection method in a such a way that we are going to get only the topmost value. So we don't want to get the bottommost value, we are going to get the values with the greater fitness value. So that is why I'm sorting the value. After sorting the value, I'm sorting, how am I going to sort my value? I'm going to sort my value based on my fitness value, right? So the whatever the individual or whatever the base is going to have a higher fitness value will be come in the top. So that is why I make the reverse as true. Okay, if you're trying to sort, it basically takes the ascending to descending value. If you give the parameter reverse as true, it will be reverse the value. Basically, it's going to sort in a way that your higher values will come first and lower value will come in the bottom. So that is what we are going to do. Okay, now I'm going to run for the epochs. Initially, we are going to do a random selection. Why we are going to do a random selection? We are selecting the parent, right? So first method is we need to select the parent. How we are going to select the parent? We are going to select the parent in a random function. Next one is like crossover. What is a crossover? Crossover, like now we are going to move into the helper function. What helper function says that, okay, fine. So random selection, the parent selection is like, sorry, this is not a random one. We are going to select the parent in a highest performing individual as a parent. So we are going to select the parent based on the fitness value, right? So rank based selection. So in here, if you see this particular for function definition, you see the population. This population is nothing but your current population. What is the current population? Current population is a sorted population. So sorted population in the sense, you're going to have your highest fitness value as a topmost one as compared to the lowest fitness value. So there's a sorted value, right? So if I give a sorted value and I'm going to take the pool size, what is the pool size? Number of individuals is going to the pooling or mating process. So that is what a pool size. In this case, we mentioned 20. We are going to take only the top 20. So the top 20 in the sense, right? You're going to take the top 20 set of weights value, which produces a higher fitness value, higher accuracy. So that is what we are trying to do in this particular random selection method. Okay. Now I selected my random pool. I am selected my mating pool. Then what I'm going to do after selecting a mating pool, I need to go for the crossover operation, right? So if I go into crossover operation, I need to define a function for the crossover. This crossover is a double point crossover. I'm going to just select the random points. Like I'm going to select a random indices. After selecting a random indices, like I'm going to take the values of the first index to last index and last index to first index. So this is what we're trying to do. And we're just going to multiply with some random value. That is a tweaking values. So you can trying to figure out, like you can trying to play using a different crossover functions. So this is a basic one. You can try to figure out different values. That is up to you, right? So you can choose on your own. You can also you can also comment it out, comment this out and comment this out. You can try to play and see how the results changes. So this is what we are trying to do in a crossover operation. After crossover operation, you just add it to the mating pool. Okay. Next one is like your mutation operation. After crossover, we're going to perform a mutation, right? So this mutation operation says that I'm going to randomly tweak my population. How am I going to randomly tweak my population? I'm going to pick a random value. So this random value will have a lower range of 0.75 and higher range of 1.25. This is not like what to say. Excuse me. This is not the fixed value. You can take -5 to +5. This is up to you guys. So this is an hyperparameter. You can play with it and you can give a proper documentation what you're going to do based on the results you're going to perform. So I'm taking 0.75 and 1.25. This is not mandatory. You also supposed to do the same kind of settings. You can also do it on your own. Okay. So you're going to take a random value, and after taking a random value, you're going to multiply with your children. That is, you're going to multiply with each and every cell. So to be precise, let me show you in the slide. Okay, see, in this case, we selected this pool and we just multiply some random value with the selected indices or all the indices. So that is what we are trying to do in the mutation operation. Now, the next is here comes the most important part. There is a replace population. Okay, now the replace population says is going to like mirror your this step based on a fitness value calculation. You're going to replace the sum of the chromosomes over here with a new set of chromosomes or new set of offsprings. How we are going to do? So that is what the helper function replace population is going to do for you. Okay, replace function says that, okay, initially I'm appending all my child and current population. Okay, so initially I appended all my child and current population, but what my rule says, if I have a 300 or if I have 500 size, I need to retain 500 size throughout my algorithm. I don't want a 500 plus 2520. So that is what needed. I need to eliminate the 20. How am I going to eliminate the 20? I'm going to sort the fitness value in a reverse order and I'm going to remove the bottommost 20 value. So that is what I'm trying to do in this particular place. Okay, so this is a replace population. Now I'm going to take all this, I'm going to take the current position of 0. Why I'm telling current position of 0? Because I'm sorting my current position, right? If I'm trying to sort my current position, I'm going to take only the first value in my current population is the best individual. Why I'm telling a best individual? Because that individual is going to produce my maximum accuracy. So that is for the best individual. Okay, so I'm going to take it as 0 because the index start from 0, and for that particular individual I'm showing the fitness value, I'm showing the accuracy. Okay, if I run this, You can see 0.96259135. It's 60, guys. It's keep on increasing over the iterations. For example, if you take some randomly 100, okay, see this 71, 72, 74, 76, 77. That is also evolving, right? If you take the last one, see, there is a poor performing weights. Okay, so we'll always try to take the best performing weight. So that is why I take the first value. So just keep on increasing and keep on iterating. So 0.86 and 0.96. Okay, so then you can benchmark using the classification report. Guys, you can see this, the one which has a least value, right? This is because this is an imbalanced data set. You can try to oversampling techniques, undersampling techniques that you can try to avoid, or you can also use an variational auto encoders, so to figure it out to get the excellent values. Okay, so just a promo kind of things. So we are from the coding club, we are trying to solve many problems, like many hands-on sessions for you guys. So if you're interested, kindly follow the coding club pages, okay, Instagram handle, as well as we will also in our GitHub. You can follow us there also, right?